Hi, everyone. In this lecture, we're going to continue comparing the relationship between the mean, the median, and the mode. So in the previous lecture, I taught you how to find the mean, the median, and the mode, both by hand and the calculator. But now I think it's really important that I go over how we interpret the mean, the median, and the mode in context with one another and in the context of a particular problem, and when one might be a better measure than another. So let's talk about a couple of things first, and then we'll do an example. Let's talk about the word resistant. When you resist something, you don't want to change, right? You want to stay where you are. So we call a measure a resistant measure if its value is not affected by an outlier or an extreme data value. So remember in chapter 2, we did go over the definition of an outlier. An outlier is just an extreme value in a set. It could be extremely higher or lower than the rest of the data values in the set. Now, if there's an outlier in the set and it doesn't affect a measure of central tendency, then we call that measure resistant. Now, the mean is not a resistant measure of central tendency because it can't resist the influence of extreme data values in a set. And you're going to see that in the example we're going to do in a minute, example 4. The median, however, is resistant to the influence of extreme data values or outliers in a set because it doesn't respond strongly to the change of a few extreme data values, regardless of how large the change may be. And let's talk about the mode for a minute. The mode has an advantage over both the mean and the median when your data is categorical, because when you have categorical data, it's not possible to calculate the mean or the median because you need numbers. You need numerical data in order to calculate the mean or the median. So whenever you have categorical data, the mean or the median doesn't exist, only the mode would. So the mode would be a good measure of central tendency for categorical data. So we're going to look at the difference between when we should use the mean, the median, and or the mode as the best measure of center. And I think example 4, this next example, does a really nice job illustrating that. So let's look at example 4. So it says, and we'll make this a little bit bigger. The following data values represent a sample of real estate listings for homes in Massapequa, New York. So we have 1, 2, 3, 4, 5, 6, 7 listings here. So 7 prices of houses that are for sale. So what I want you guys to do is calculate the mean, the median, and the mode for these prices for this set, this sample. So we're working with a sample. Now you can pause this if you'd like and practice doing this on your own, because in the previous lecture, I did an example where you had to calculate the sample mean, the median, and the mode. So if you want, you could pause and try doing this on your own and then comparing your answers to mine, and then we'll talk about it. So I'm going to calculate the mean first. So X bar is the sample mean. Then we're going to list the median. And then I'm asking you also to find the mode. So you should have, at the very least, at least paused and entered these 7 listing prices into your calculator, into a list. And I'm going to share my calculator with you because I already did so as well. So I'm going to press stat and edit. And you could see where I put my list that my house prices are here in L3. There's my 429,500 and 465,000 and so on and so forth. So my home prices are in L3. So remember, if we do a one variable stat or one var stat, like I showed you in the previous video, we could get the mean and the median in that output, right? So I'm going to press stat over to calc. And remember, it's option 1, one var stats. You have to tell the calculator what list to use. I want my calculator to use L3, so I'm going to change that to L3. Remember, leave frequency list empty, and then we're going to calculate. So we're going to hit enter. So the first thing that pops up is the sample mean. So that's $759,542.86 if I round to the nearest penny. Now scroll down because we want the median also. So the median is equal to 549,900. So let's write those down on the worksheet. So the mean is equal to $759,542.86. And the median is equal to $549,900. Now, there's not that many data values in this sample. There's only 7. So the mode will be pretty easy to find if there is one. So what we're doing is we're scanning right now to see if there's any listing price that repeats itself more than any other in the list. And there doesn't seem to be. So there is no mode in this case. So just write none. There's no mode. It's non-modal. So really the only 2 measures of center that we have right now for this data set are the mean and the median. Now, before we get to, well, let's look at part B. So, well, no, before we get to part B, I want you to look at the mean and the median and say, okay, what seems to be kind of off a little bit, right? Because if they're both measures of center, wouldn't you expect them to be similar or the same, right? If they both fall in the center. But if you look at them and compare them, they're way off from each other, right? There's a difference of almost $200,000 between the median and the mean, right? The mean is about 759,000. The median's 549,000. That's a difference of like $200,000. That's a big difference. That's a lot of money. It's not like we're talking 2 or 3 cents or $2 or $3. So now the question becomes, why is there such a big discrepancy between the median and the median if they're both measures of center? And then which one then would be the better measure of center? So that's why I asked about part B. So part B says, which measure is a poor measure of central tendency, and explain your answer. So if imagine you're the real estate agent and I'm your customer, I'm your client, and I'm looking for a house in Massapequa. And I ask you, my real estate agent, to tell me what's like the average price of a home, right? What's the average selling price of a home right now in Massapequa? What are you going to tell me? Are you going to tell me it's 759, 542, 86, or are you going to tell me it's 549, 900? So I want you to think about that for a minute. And if you have to pause and think about it, that's fine. But the correct answer is, if you're the real estate agent, you're going to tell me what the average price of a selling price of a home is in Massapequa. You're going to tell me it's about 549,900, not 759, 542, 86. And this is the reason why. If you scan, just scan with your eyes these listing prices here, they're all pretty much relatively close to one another. You have 429, 465, 359, 629, right? There's not that much, craziness in the numbers going on here. But then we get to this listing price of $2.3 million. That is way bigger than all the other prices, right? It's way higher. So we consider this extreme value an outlier since it's not in line with the rest of the selling prices, right? That's way above. That's an extreme value. So the reason that the mean is so much higher than the median is because to get the mean, we had to add up all these home prices or listing prices and divide by 7, right? So that 2.3 million was part of the sum. So that's why the mean is so much higher than the median. But if you had to pick the mean or the median is going to be more in line, right, with the rest of the data values. That 2.3 million, right, is an extreme value. And that's what's driving up the value of the sample mean to 759,542, which is higher than all of these listings, right? Except for the 2.3 million. So the measure that's going to be a poor measure of central tendency, the one that we don't want to use as the average in this case, is going to be the mean. So the mean is a poor measure of center, and I want you to explain what's the reason. And the reason is because the mean is not resistant to outliers. Whereas the median is, right? So that $2.3 million affected the mean. The mean couldn't resist that extreme value. So it couldn't resist the outlier in the set. So the mean is going to be a poor measure of center for that reason. So we would use the median in this case as the best measure of center, or the best representative value of a selling, a home selling in Massapequa, New York. So I think this is a great example comparing the different measures of center and when we would use one over another. So let's look at one more example in this lesson. So example 5. So I gave you 3 different distributions here. The one on the top left is bell-shaped, right? Here's a bell-shaped distribution. The one on the top right is skewed. And it's skewed to the right, right? Because the tail tapers to the right. And then the one on the bottom is also skewed, but it's skewed to the left. So we have these 3 different distributions. And what I want you to do for each of them is I want you to tell me where the mean, the median, and the mode would be within these distributions. So let's start with the bell-shaped distribution, or the symmetric, right? Bell-shaped is the same thing as symmetric. Now, what's nice about a symmetric distribution, as you can see, is the peak is right in the middle and it splits the data evenly in half, right? So we could see where that dashed line is. That's the center of the distribution. And it's also the highest peak. So the bell-shaped distribution is always going to have the mean, the median, and the mode right in the center. And they're all going to be approximately the same. They don't have to be exactly equal, but they're going to be very close. So we say that the mean is approximately equal to the median, which is approximately equal to the mode whenever we have a bell-shaped distribution. The 3 of them are going to be in the center. Because think median is the middle value and the mode is the number that occurs the most frequently. So that's where we're going to have the highest peak. The mode is always going to be at the highest peak. So the bell-shaped one is easier to remember, I think. It's more obvious. Let's look at the distribution now that's skewed to the right. Think about why it's skewed to the right. So this is where most of our data tends to cluster under this curve, right? There's not a lot of data out here in the tail. And the reason for that is because there's probably extreme values or an outlier out here, far away from where most of the data tends to cluster, which is here. So whenever we have a distribution that's skewed, whether it's to the right or to the left, it's because there's extreme values in the set. So in this case, the extreme value is going to be higher than the rest of the data values. Because think of the horizontal axis as a number line. X is smaller than Y, Y is smaller than Z. So this is just a number line. So out of X, Y, and Z, which one's going to be the mean, which one's going to be the median, which one's the mode? Well, I always think the mode is the easiest one to spot because it's the highest frequency, the data value that occurs with the highest frequency. And that's going to be where the peak is, the highest peak, which is at X. So X is going to be the mode. Now we have Y or Z. Which one's the median? Which one's the mean? Well, I think the median's easy also because the median is the middle data value in the set. So Y is right in the middle, right? Between X and Z. So Y is going to be the median. And think of it as the balancing point of this distribution. So it doesn't wobble. Imagine that blue line that I just drew is a stick, and this curve is kind of balancing on it. It's not going to waver back and forth because it's in the middle. And think about the example that we did above with the house prices. Remember, the mean can't resist outliers. The mean is going to be affected by outliers. Now, we have an outlier in the set up here, right? We have an extremely high data value up here. So that's going to affect the mean. The mean is going to be drawn closer to the value of the outlier. So Z is the closest data value, right, out of the three to the outlier. So Z is going to be the mean. The mean is always going to be closest to the potential outliers because the mean can't resist. So that's the relationship between the mean, the median, and the mode in a distribution that's skewed to the right. Now the mode is going to be smaller than the median, and the median is going to be smaller than the mean. Because remember, this horizontal axis represents the values of our data set, but they go in increasing order from left to right. So the mode is going to be less than the median, and the median is going to be less than the mean. And that's their relationship. Now it's going to be the opposite in a distribution that's skewed to the left. So now in a distribution that's skewed to the left, most of the data values are going to tend to cluster to the right, to the higher end, where the data values are higher in nature. And you're going to have your potential outliers at this end of the distribution, where the values tend to be lower in nature. So out of the 18, 19, and 20, which is the mean, the median, the mode? So the highest peak is going to be the mode. So 20 seems to be the data value that occurs the most frequently because it has the highest peak. So 20 is going to be the mode. The median is the number right in the middle of the set, which appears to be 19. 19 is in the middle, so that's going to be the median. And again, remember, the mean is going to be closest to the potential outliers in the set because the mean can't resist those extreme values. So 18 is closest to the outlier. So the 18 is going to be the mean. And we could see 18 is less than 19 and 19 is less than 20. So the mean in this case is going to be less than the median, which is less than the mode. And that's the relationship between the mean, the median, and the mode in a distribution that's skewed to the left. So in the next lecture, we're going to continue on with section 3.2, and we'll talk about measures of spread and deviation.